Areas of regular polygons, day one. We're going to be talking about squares, triangles, and hexagons today. First thing we got to cover is the different parts of a regular polygon that we're going to be referring to. We're going to be referring to the apothem. The apothem is the distance from the center of the polygon to the midpoint of a side. So that means those two parts of our side of our polygon are going to be congruent. We're going to be talking about the radius. The radius of the polygon goes from the center of the polygon to the vertice of the polygon. It is the radius of the circle that is circumscribed about the polygon. So you can see here that that distance is also the radius of the circle in blue that I have drawn out there. Two other things that we're going to be talking about or referring to is the perimeter of the polygon and the side length of the polygon, which I believe are two pieces of prior knowledge that you should already know. So when we start looking at the area of a square, we need to recognize what type of a square problem are we looking at. Are we looking at a problem that makes reference to the diagonals of the square, or are we looking at a problem that references the lengths of the sides of a square? So here we're looking at the diagonals. Here we're looking at the side lengths. If we're starting with a radius of a square, like I have drawn here on the left, we are going to be using the diagonal formula. Our diagonal formula, just to remind you, is 1/2 diagonal 1 times diagonal 2. If we are given either an apothem or a perimeter, we are going to use our side lengths. Our side length formula for a square is simply the area equals the base times the height. Now if they give us an apothem, say our apothem here is 3, that means our side length would have to be 6. Because if our apothem here is 3, from the center down to that midpoint is 3, if I were to draw in another apothem up on the top, that length would also be 3, which is where we get our 6 from. So here's our first example of a square. We're going to find the area given the perimeter. If we have a perimeter of 48 inches, that means the first thing we would need is the side length. So to find our side length, we would simply take the 48 inches, that is our perimeter, and we're going to divide it by 4 because the square has 4 congruent sides. That would give us each side length at 12. That gives us enough to use our area formula using the base times height version. So area is equal to 12 times 12. And we are looking at 144 square inches for our area of that square. Our next example of a square is when they give us the apothem. So if they give us the apothem, which is 6 inches, we talked about 2 slides ago that if this apothem is 6 inches, our second apothem from the center to the exact opposite midpoint would also be 6 inches, which gives us a total length here of 12. Being a square, if that's 12, our side down here would also have to be 12. That gives us a base and a height of our square, enough to finish off our formula using base times height. So again, we ended up with 12 times 12. Just a coincidence that we ended up with the same thing again. And we get 144 square inches for our answer for the area of that square. Now if we have a radius, radius indicates that we're going to be looking at the diagonal because the radius is a part of the diagonal. There's our diagonal right there. You can see that the radius is a part of that line. So we're looking at using the area formula, that is 1/2 diagonal 1 times diagonal 2. If this radius here is 10 inches, that means the radius from here to the other corner is also going to be 10 inches, which gives us the full diagonal length of 20 inches. So we're looking at our area being 1/2 of 20 inches times the other diagonal. In a square, the diagonals are congruent to each other, so this diagonal here would also be 20 inches. We simply finished solving this, 1/2 of 400. And our area would be 200 square inches. Here we're going to start to look at the area of equilateral triangles. We're in a unit where we're looking at just the regular polygons. So we already did the square, which is a regular quadrilateral. We chose that one first because it didn't deal with the special right triangles. But we're going to take a step backwards and look at equilateral triangles, which is a regular triangle because all three sides are equal and all three angles are equal. First thing you need to do is you need to recognize your 30, 60, 90 triangles that are inside of our equilateral triangles. You can see down on the right that we have a 30, 60, 90 setup if we draw an altitude down from the top vertex of an equilateral triangle, because this full angle up here, remember, is 60 degrees. So the altitude cuts that angle in half, creating our 30-degree angle and allowing us to have our 30, 60, 90. And then we just have to make sure that we get our rules, the 2x, the 1x, and the extra 2 in the correct positioning. Now the funky thing about this is the same thing happens when we look at the apothem. Over here on the right, we look at the apothem of the triangle and the radius of the triangle. The radius of the triangle also cuts that 60-degree angle in half, giving us that 30-degree angle over there. So we end up having our 30, 60, 90 down there in that corner also with a 2x, 1x, extra 2 relationship. So let's use that information to help us find the area of an equilateral triangle. Being that these are triangles, we are going to stick with our normal triangle formula for area, which is 1/2 the base times the height. So if we have a perimeter of 60, if we divide that by 3, that gives us each side length of 20 inches. So if that's 20, and we have a 30, 60, 90 triangle right here, our rules are 2x, 1x, and extra 3. If this side here is 20, this side down here has to be 10, which makes complete sense because if that side's 10, we have 10 over here for a full side length of 20. Now if x is 10, that means our extra 3 side is going to be 10 root 3. So what that gives us is that gives us our height, which is 10 root 3, and our base, which is 20. So if area equals 1/2 base times height, we're sitting with 1/2 20 times 10 root 3. So half of 20 would be 10. 10 times 10 is 100. So we're looking at 100 root 3. And we have our answer of 173.2. That would be in square inches. All right, next problem. We're going to look at an equilateral triangle with a radius of 10 inches. So our radius right here is 10. We need to recognize that we have our 30, 60, 90 relationship right here. So if that's 10, our apothem is 5, and this part of the triangle would be 5 root 3. So if that's 5 root 3, we know that the apothem goes to the midpoint, which makes the left side of this also 5 root 3, giving us a complete side length of 10 root 3. That would be our base. Now our height, however, we only have the apothem here. This goes from the center to the midpoint. Going the other direction, though, goes from the center to a corner. We call that the radius. We already know the radius because that was given to us down here. The deal with a radius or an apothem within a regular polygon is every radius is the same length and every apothem is the same length. So if we already have a radius of 10, that means our radius up on the top here would also be 10, giving us a full height of 15. That's the 10 plus the 5, the radius here, plus the apothem down here. So we have enough information to use our formula for the triangle. 1/2 base times height. That would be 1/2 of the base, which is 10 square root 3, times the height, which is 15. So 1/2 of 10 would be 5. 5 times 15 would be 75. Square root 3, we can go ahead and calculate that out. (75 root 3) gives us 129.9. Square inches. That would be the area of our triangle, or equilateral triangle, with a radius of 10 inches. Our final equilateral triangle example starts us off with the apothem. In this problem, we have an apothem of 6. We know we have our 30, 60, 90 rules. If that apothem is 6, that means our radius would have to be 12 by following our 30, 60, 90 rules. And our 1/2 a side length here would be 6 root 3. If that 1/2 a side length is 6 root 3, that means our full side length would have to be 12 root 3. So we have our base. Looking at our formula, area is 1/2 base times height. We have our 1/2. Our base is now 12 root 3. We just need our height. So our height is made up of the 6, which is the apothem, and then we have our radius right here. Well, we have a radius down here that's 12. We said every radius in a regular polygon is going to be the same length. So if we have a radius of 12 there, that means we have a radius of 12 up on top. So if that radius is 12, that gives us an overall height of 18. That's 12 plus 6, the radius plus the apothem. So we can go ahead and put that 18 in there. And let's see, we got half of 18, which would be 9. 9 times 12, that'd be 108. Square root 3. Go ahead and calculate that out. That puts us at 187.1. Square inches would be our label. And we're all set to go with our equilateral triangles. You should have one of each of the possible examples that you will run across. The last shape we're going to look at today are the hexagons. The reason we look at those hexagons is because they also include the 30, 60, 90 triangles. The deal with all the shapes that we chose today is that they all are special situations, which can be made a lot easier by knowing some of the patterns that we've talked about over the past couple of units. So our formula for a regular hexagon, and really any polygon that has 5 sides or more to it, is this formula right here, which looks kind of like 1/2 base times height, but it's a little bit different. It's 1/2 the apothem times the perimeter. So two things that we need to find here is we need to find the apothem and the perimeter. But before we jump into one and try to find either the apothem or the perimeter, what we first need to do is we need to identify our central angles. So I have a hexagon drawn down here below, and in this hexagon, what I would do is I would draw in all the diagonals that I could. Drawing in those diagonals, I can see here that our central angles created, we have 6 of them. So we have 6 equal central angles. Together they all add up to 360 degrees. So what we would do is we would take 360 degrees, all the central angles together, divide them evenly by the 6 because we have 6 central angles. That tells us that each of those central angles is 60 degrees. That comes in very important here as we start to find the area of a regular hexagon. So here's our first example. We're going to be given the perimeter of a regular hexagon, and we're going to find the area of it. So our formula, 1/2 the apothem times the perimeter, we already know one of the two pieces. We do not know the apothem yet, but we know the perimeter is 60 inches. So if I take that perimeter, which is 60 inches, and divide it by 6, because we have 6 sides, that means each side would have to be 10 inches long. So that means that's 10 inches. Because the apothem from the center to the midpoint goes to the midpoint, that means that full side is 10, making this length here 5 inches. Now that's going to help us out dramatically. Also remember, we found our central angle is the 60-degree angle. Now the apothem is a little bit interesting because that bisects the central angle. So if this angle and this angle add up to 60 degrees and it's a bisect that gives you that 60 degrees, that means each of those would have to be 30 degrees each. If that's 30 and our apothem forms a 90-degree angle with this side, that means we have our 30, 60, 90 again. If we needed the radius, we would know that the radius here is 10. So we got our 10, we have our 5. This side here, our apothem, is going to be a length of 5√3 according to our 30, 60, 90 rules. That's the missing piece that we needed. So we have everything we need for our formula to calculate the area. Half of 60 is 30. 30 times 5 is 150√3. Go ahead and calculate that out. 150 square root of 3 gives us an answer of 259.8. Square inches would be our units, and we're all set with the area of that hexagon. So now let's take a look at finding the area of a regular hexagon that has a radius that's given to us. So if we have a radius that is 10 inches, we know that our central angle is 60. By the way, our central angles for every hexagon will always be 60 because you're always taking 360 divided by 6, which makes this angle up here formed by the apothem always a 30-degree angle, making this little triangle in here always a 30, 60, 90. So if our 2x side is 10, that means our 1x side is 5, and our x root 3 side is 5 root 3. That gives us our first piece of information we need for our formula, 1/2 apothem times perimeter. Our apothem is 5 root 3. Now we just need our perimeter. If this length here is 5, that means this length is 5, which means both of those together means every side length is 10. If we have 10 for every side, our perimeter would be 10 times 6, which is 60 degrees or 60 inches. So our perimeter is 60 inches. We have enough to go on. 1/2 5 root 3 times 60 is 150 root 3. And we calculated that here just a second ago. That's 259.8. Square inches. The difference between the last two is the first one started off with a perimeter and we worked our way around to the apothem. This one started off with a radius. That's the big difference between the two problems. Our final problem for a regular hexagon is one that starts you off with an apothem. If we have an apothem here of 6. Now we know that the central angle is 60. The apothem cuts it in half, making a 30, 60, and 90. If we follow our 30, 60, 90 rules, now our side of that triangle that's down here from midpoint to the corner is going to be 2 root 3, following our 30, 60, 90 rules. If that's 2 root 3, the left side here is also going to be 2 root 3. If those are both 2 root 3, we add them together, that means each side of this was going to have to be 4 root 3. And our perimeter would be 6 times the side length, which is 4 root 3. 6 times 4 root 3 is 24 root 3. So area is 1/2 apothem times perimeter. Our apothem we knew was 6. We started off with that. Our perimeter is 24 root 3. So let's see, half of 24 would be 12. 12 times 6, 72. Square root 3 would be our area. That puts us at 124.7. For our square inches. So to recap what we talked about today, you have your squares, where you have to make a decision. Are you using sides? Or are you using diagonals? If you're using your side lengths, you're going to use the formula base times height. If you're using your diagonals, I would use the formula 1/2 diagonal 1 times diagonal 2. For our equilateral triangles, we need to recognize our 30, 60, 90s and then use our area equals 1/2 base times height formula. And then for our regular hexagons, again, we need to see our 30, 60, 90s. Which are dictated to us by finding our central angle. And then use the formula area equals 1/2 apothem times perimeter. All right, best of luck on these assignments and getting to know these three situations. Our next lesson is going to look at when our central angle is not something that gives us a 30, 60, 90. It'll be a little bit of a more unique situation. Have a good night.